Next question. An alternating AC supply is connected to a diode and a resistor in series. An alternating supply, remember, an alternating supply is current that is changing directions continuously. An alternating supply is connected to a diode and a resistor in series. This is the alternating supply here, the diode, the resistor. Everything is in series here because current would flow, enter through everything and come back. So everything is in series. Which graph shows the potential difference V across the resistor? How across the resistor varies with time? How does the potential difference V across the resistor here varies with time? You must know that when we connect an alternating supply with a diode, we are rectifying. Rectifying means that changing the alternating current to direct current. We are simply making sure that the alternating current is now going to move in one direction only. So we are not necessarily changing its magnitude, but rather we are changing its direction. But there are two types of rectification. There is full wave rectification, then there's half wave rectification. This one with a single diode is half wave rectification in the sense that it is only going to stop current or voltage from being in the circuit, from applying on the resistor when it is moving in one direction. When it is moving in the other direction, then there will be zero. So the only sensible diagram is this one, because when this part is positive, current is flowing in the diode. When the other side is negative, current is stopped from flowing in the diode because the diode will be reverse biased. When this one is positive, current flows in the diode. When this one is negative, current does not flow in the diode is reverse biased again. Number 30, the diagram shows a circuit used to switch on a heater when the temperature drops below a certain value. And the temperature drops below a certain value. Which row shows the components that should be connected at X and at Y? Okay, so remember, we want to switch on the heater. So we are switching on the heater with a relay circuit. So because the heater is in the other circuit, this one. So the relay circuit, for it to work, there must be a current which makes this to become this electromagnet, this coil, to become a strong and powerful electromagnet. So for it, we need a bigger current to be flowing in that part of the branch. But we all know that to have more current, the resistance, of course, is already a constant in that region. So if we want more current, we need more voltage across the relay. So if we are going to connect things now, we want this to work when temperature drops below a certain value. So we want two resistors, which one of which is responsive to temperature change. This light dependent resistor cannot be part of this circuit because it serves no purpose, as it only responds to change in light intensity. So A and C is automatically wrong. So the question is, where does the fixed resistor go and where does the thermistor go? That's the only question. Now remember, we want to increase the voltage of this part here as compared to the voltage here. So, and you must also know that these resistors, the thermistor and the other fixed resistor, are going to be in series. So when the resistors are in series, for a resistor to have a bigger voltage, its resistance must increase. Now here's the dilemma now. If we were to put the thermistor here and the fixed resistor here, we know that the resistance of the thermistor is inversely proportional to the temperature. So when the temperature drops as they want there, then the resistance of the thermistor would increase. So if the resistance of the thermistor increases whilst it is here, the voltage across it would increase because it is sharing the voltage from the battery, and the voltage across the fixed resistor would decrease, meaning that the voltage across this one would decrease. So the best case scenario which will work is if the thermistor rather is here and the fixed resistor is here, such that if the thermistor's temperature decreases and the resistance of the thermistor increases, then the thermistor being here gets a bigger voltage compared to the fixed resistor which is here. And as a result, if the thermistor is getting a bigger voltage, since it is in parallel with the relay also gets a bigger voltage, and a bigger voltage on the relay means a bigger current. A bigger current means that the relay becomes magnetic, and when the relay becomes magnetic, then it is able to close the circuit of the heater, and the heater is switched on like that. So the current, the answer is B because of that. Then the next question is 32. A metal rod PQ rests on two horizontal metal wires that are attached to a battery. The rod lies between the poles of a magnet. It is resting on two horizontal metal wires that are attached. Resting meaning that it's not moving, that are attached to the battery. The rod lies between the poles of the magnet. When the switch is closed, the rod is moved to the right. So what happens when the switch is closed? When the switch is closed, there's a current in the rod. And when there's a current in the rod, it moves to the right. What could be changed so that the rod moves to the left? So if you want the rod to be moving to the left, what can we change? Now there are several things we can change. The reason why the rod is moving to the right here, for example, is because of this. The battery is positive here, so current will flow like this and into the rod like that. So current in the rod is in this direction, and the magnetic field of the magnet is in this direction. So by Fleming's left-hand rule, the force on the rod when there's a current is to this direction. So if we want the force on to change to come to the other direction, we have to change either the current or the magnetic field of the magnet. That way we can change the direction of the force on the rod. So A says open the switch, there will be no current, so this does not change current. Reverse the battery terminals and exchange the poles of the magnet. This will cancel out because reversing the terminals of the battery, then of course that will change the direction of the current. But however, if we also exchange the poles of the magnet, then by Fleming's left-hand rule again, the force will be to the right. Reverse the battery terminals without exchanging the poles of the magnet. Now, this changes current alone without changing the direction of the magnetic field. So this alone, by Fleming's left-hand rule, will produce a force now to the left. Then the next question says, a radioactive isotope X decays to the stable isotope Y. The graph shows how the mass of Y present in a sample varies with time. So this graph is actually showing us how the mass of Y present in a sample varies with time. Which time interval gives the half-life of X? Now half-life, remember in this case, this is a graph of Y which is being formed from X, which is decaying. So half-life by definition is the time for nuclei to decrease by half. But in this case, since this is a graph of Y which is being formed, half-life will be the time taken for Y to increase by half. The maximum value of Y is going to be M. So if it increases from 0 to half, M over 2, then the time taken there is T2. So that's there is our half-life. So